We'll talk about Bernstein theorems for prescribed mean curvature.
Okay, thank you. Thanks, Davi. Thanks, Jorge. Thanks, Walcy, for the invitation to speak at this Congress. It's always a double pleasure to be here in Brazil, to come back. And the purpose of this talk is to study. This is part of a joint work with Bruno Bianchini from Padua, Marco Rigoli from Milan, and Patrizia Pucci at the University of Perugia. The setting will be the following. We have a complete manifold, Mg, in an ambient space, and we study graphs, entire graphs with prescribed mean curvature. Let's say in a good ambient space, so our ambient manifold will be fibered via geodesic. So we have an ambient manifold which is a product which is warped via a function, a warping function h, and the product can be written via a change of parameter on the geodesic as a conformal deformation of the standard Riemannian product, with T is just a reparameterization of the geodesic. And so we will study entire graphs of function u of x defined on the entire M. Slices will be considering the variable t. And it turns out that if one computes the mean curvature of an entire graph, the expression, one arrives at a quasi-linear PDE of this kind, equal to m lambda of u h plus a function here f of u, where f of u is the logarithmic derivative of the conformal factor. Okay, we aim to investigate in this setting entire minimal graphs, or also entire graphs whose mean curvature is prescribed as a function on d8, so kind of a weight acting on the manifold b of x times a function on d8. Typical case is the capillarity equation, where the weight is constant and f of u is equal to u. Classical equation modeling a surface subjected to tension and both the action of gravity. But it turns out that the equation that we will deal with allows application to mean curvature soliton in those ambient space. Where with a soliton, suppose that your entire graph moves via mean curvature flow. That has been defined in previous lectures. And we say that this is a soliton if there is a vector field in the ambient space such that the movement by mean curvature is induced by the flow of this vector field up to a time reparameterization. And it turns out that, for example, in this case, if the vector field is the vertical vector field dt, one still has an equation of this kind, over the square root is equal to another function, f of u, still over the square root 1 plus grad u squared, where f bar of u is just a modification of the previous f of u. So in the case of a Riemannian product, minimal graphs, we just have 0, we have the familiar mean curvature equation. Okay, what is known? And our purpose is really to investigate the PDE and try to get a Liouville theorem with as less information on the underlying manifold M as possible, typically with a volume growth requirement, so no curvature assumption. What is known in the case of Euclidean space? Well, there are various classical results. Of interest for us will be mostly the first and the third. It's a result by Chen and Flanders that if you have a graph with prescribed mean curvature, h, then the mean curvature shall decay faster, at least as power 1 over r, along some sequence. So in particular, if the mean curvature is constant, classical result, the only entire minimal graph has to be, every entire minimal graph has to be minimal. Or there's the celebrated Bernstein theorem up to dimension 7. Entire minimal graphs are affine up to dimension 7. And of interest for us will be the paper Bombieri, De Giorgi, and Miranda in 69, who, as a consequence of a Harnack inequality, proved that entire solution of the minimal surface equation in the Euclidean space, which are positive or bounded on one side, are necessarily constant. Okay? So, but on the other hand, what happens in the hyperbolic space case? In the hyperbolic space, the hyperbolic allows interpretation as a Warped product in two different manners. One is as a fibration over a horosphere along geodesic lines. And here, h of s is e to the s. And another is a fibration in the upper half space model via hyperspheres along geodesic lines. So here, m is hm. And as the beautiful result states the following. In any dimension, there exists no entire minimal graph over horospheres, and the only entire minimal graph over a hypersphere is the neck of the Warped product. That means the totally geodesic slice, the only totally geodesic slice. This has been proved, actually a more general result, as an application via nice use of the moving plane method. So it uses a lot of, okay, the result is more general, but it uses a lot on the underlying ambient space, the existence of many geometries. And in the other case, just let me write down h of s is the hyperbolic cosine of s. Okay, what does it happen in the case that we prescribe the mean curvature in the Euclidean space? There's this beautiful result due to Vladimir Kirchhoff in 92, later reproved by Naito and Ozami with a different technique in 97 and extended. Kirchhoff's proof has been extended by Jenseri. So prescribe the mean curvature as a non-decreasing function on the 8 times some weight. If the function is not identically 0 and the weight does not decay, decays slower than linearly, so power r to the minus 1, then f of u is identically 0. And since f is not identically 0, u has to be bounded on one side, and you apply Bombieri, De Giorgi, and Miranda to say that u is constant. Okay? And the result is sharp since for f equal to 0, there are affine function. But the result is not sharp if f has some specific structure. For example, in this case, you can find applying to the capillarity equation b of x constant f of u equal to u, global solution of the capillarity equation, the only global solution is u equal to 0 in Euclidean space. But actually, for example, for the capillarity, the bound on B is not sharp. So it doesn't, this proof doesn't see actually the real shape, the shape of F in a sharp way. But the proof is very elegant and very simple. You just fix a big parameter, alpha, a cutoff function of the ball of radius 2r into the r into the ball of radius 2r, and plug distance function, appropriate power of f of u, into the equation. So on the right-hand side, into the weak definition of the equation, on the right-hand side, you have a positive quantity, and on the left-hand side, two terms that comes from differentiating psi and differentiating f. But this term is thrown out by the monotonicity. You just have the term differentiate containing psi, and you throw out this term by the boundedness of this quotient. When you arrive here, you simply apply Holder inequality to recover again the left-hand side. The price to pay is a power of b, negative power of b, times a negative power in here. You rearrange, and you just choose correctly the cutoff. So the cutoff is something decaying like t to the alpha in a bounded region and rescaled, so composed by the distance function r of x divided by r. In this way, the cutoff, these terms throw out r to the minus alpha in the denominator, and you compute the integral, and you simply have a power of r. And if alpha is big, this power, since mu is less than 1, if alpha is big, this power is negative. And let r go to plus infinity, and the left-hand side goes to b f of u to the sigma, and you get 0. Just some remarks on the proof. The monotonicity of f is crucial to throw the term that actually helps. But on the other hand, it just uses the volume growth of balls in the Euclidean space. Okay? Nothing of the structure. But polynomial volume growth is crucial to conclude. Otherwise, you cannot conclude. And suppose further, in the case when, where's the eraser? Okay. In the case when f of t has only 1, 0, that for easiness we placed as in 0, the result is actually can be restated as a result just for subsolution. The only non-negative subsolution of this PDE in the Euclidean space is 0, provided that B does not decay too fast. Well, this statement is in sharp contrast with what happens for other operator, for example, for the Laplacian. So the mean curvature from this point of view is very special. Because for the Laplacian, it is known that under the same condition on f, if you want to study non-negative subsolution of this object, and the weight does not decay faster than quadratically, and this is sharp, then the only subsolution is u identically 0 if and only if f grows sufficiently fast, where fast means faster than linearly. Okay? You take the integral of f and you construct this condition. So if f is faster than linear, this is faster than quadratic, and this is faster than linear is integrable at infinity. This is called Keller-Osserman condition. It's a very celebrated condition. But for the mean curvature operator, so there is no Keller-Osserman condition, it seems. Well, actually, it is false. There exists a Keller-Osserman condition. Nobody, I do not know its expression, but there is a threshold for f in order to have a Liouville theorem. And we will see it in our main result. It's kind of strange. Let me skip this slide, or let me do this slide very briefly. Why there is no Keller-Osserman condition for the mean curvature? I try to explain a reason why. So suppose that you have a quasi-linear operator written in this way, where for us, phi of t will always be t over the square root of 1 plus t squared. So phi is a non-decreasing, strictly increasing, positive function, which is 0 at 0. Okay? Well, the Keller-Osserman condition is related to the Pre-Legendre transform of this function, identifying the quasi-linear operator. And if the Pre-Legendre transform that realizes a homomorphism onto some interval is onto, then you can define a sort of Keller-Osserman condition, and it turns out it's the right one. So basically, it's interesting to see how it interacts to geometry to give a Liouville theorem for non-negative solution. But basically, this condition, let me say, it's always necessary, and under suitable geometric condition is also sufficient. Okay? But for the mean curvature operator, the Pre-Legendre transform is not onto. So you cannot even define the Keller-Osserman condition in this sharp way as it is usually defined. This is known since, you can find a very beautiful treatment in the book by Patrizia Pucci and Jane Serre in 2007. It's a sort of Bible of the maximum principle. So first observation, what happens in the case of a product? So when f is equal to 0. When f is equal to 0, there's this nice result that is due to Rosenberg, Schutz, and Spruck in 2013. If the underlying manifold, always complete, has no negative Ricci curvature, and in their theorem, the sectional curvature is bounded below by a constant, then positive graphs are constant. Okay? Well, actually, one can play with a proof and almost remove somehow the assumption with a quadratic decay on the sectional curvature. No, decay on the sectional curvature no faster than quadratic. as far as I know, it's an open problem. It seems not an easy one to prove the theorem under the only condition on the Ricci curvature. So whether the Bernstein theorem holds under the only condition on the non-negative Ricci curvature. And the first question is, can one obtain in the minimal case, so phi Laplacian of u, here I write phi Laplacian of u to shorten, as a shortening, but I always mean mean curvature operator. I just write down here the general expression, but whatever. It means always keep in mind just the mean curvature operator for this talk. This theorem does not admit a generalization to under volume growth assumption. There's almost no way. And there's a simple example why this should be true. So suppose that you want to try to prove constancy of positive entire minimal graph under volume growth condition. Take the base manifold, which is a Warper product of this kind. It grows linearly from both sides. This is M itself. Well, actually, you have, in dimension big or equal than 3, you can build up very simply a positive bounded solution of the minimal surface equation. And the manifold has a lot of beautiful property: polynomial volume growth, quadratic decay of the sectional curvature. So really, and dimension 3 is essential for this integral to converge. But otherwise, with quadratic volume growth, you are in a regime of parabolicity, so everything is much easier if the volume growth is quadratic. So what is let us state our theorems, and then we will see how they apply to the examples and to entire minimal graphs in Warper product. We will study, let's say, mean curvature operator, a continuous function f, and an expression on the gradient. L of t is basically phi of t over t to the key. That means t to the 1 minus key over the square root of 1 plus t squared. In the case of minimal graphs, entire minimal graph, you have this term on the right. So it corresponds to the case key equal to 1. But it's useful to allow key to vary in between 0 and 1. And b of x is basically a power minus mu of the distance. Okay. So if you have a subsolution, what's the first result? The first result is the following. Suppose that your f does not need to be in a monotone, increasing, but it grows faster than some power, omega. And this condition relates the decay of b, which must be not that much, with the volume growth of the geodesic sphere. Note that the bound here is exponential to r to some power. So it's quite big volume growth. And in the borderline case, we have a polynomial volume growth. Suppose that this condition, any of these conditions is satisfied. In the case of graphs, basically there is no mu. Mu is 0, and key is 2. So we are by far in this regime. If omega is bigger than key, then any solution, any subsolution is bounded above, and f of u star, where u star is the supremum, is less or equal than 0. So in particular, as the function is non-negative and f is positive, for u positive, you have a Liouville theorem. U is identically 0. Note that everything in this theorem, the parameters are sharp, and also the condition here. And this is a growth condition on f. So this is a Keller-Osserman condition. It actually appears a Keller-Osserman condition also for the mean curvature operator. Why you do not see it in the proof of Kirchhoff in the polynomial case? Well, that's because if you want to redo the proof verbatim in the setting of when a gradient dependence is allowed, the proof of Kirchhoff just works when the gradient, the function L here, is when key is equal to 0. So we are in a borderline case. And in this borderline case, key equal to 0, the condition gives precisely mu less than 1. But here you allow exponential growth, and you have w greater than 0 here. Basically, in Kirchhoff, you have a polynomial growth and no condition here. But you really need, even for key equal to 0, if the volume growth is allowed to be exponential, you really need a Keller-Osserman. So the result actually matches somehow, glued together in a strange way. Okay, and the other result, and this is related. I mean, various people worked on this. I just single out works by Enzo Mitidieri and Lorenzo D'Ambrosio, Roberta Filippucci, and Farina and Serrin. These are 2012, and more or less 2012, more or less the same period, where equations of key is the parameter in the degeneration of the gradient term. So you allow this term not to be, if key is equal to 1, you have exactly 1 over the square root, which is the case of the graph. But it's useful to allow key to vary. And we'll see this just in a moment. And note that the gradient term can vanish both in 0 and at infinity. So you have the generation of the gradient term in 0 and at infinity. The second theorem states the same kind of has the same conclusion, but now f does not vary, does not grow. Basically, it just stays above some constant at infinity. But u is supposed to grow not that much. And again, any parameter here with the volume growth matches in a sharp way. So, for example, what does the result say about the capillarity equation? If you have a capillary equation on a manifold, well, previously, basically, the only result was known, actually the only result known was Kirchhoff's theorem. If B of x times u, if B decays as a power r to the minus mu, where now mu can be less than 2, and the volume growth does not grow faster along some sequence as an exponential to power 2 star minus mu, then u is 0. So in the original capillary equation, B is constant. Actually, the growth allows 2 star means any number less than 2. So the volume growth condition is a quadratic exponential, the threshold. It's not polynomial. It's much more. And this is a strange thing because it's a curious example of how worsening the equation allows to get a better result. Because if you have this equation, you simply introduce artificially a gradient term. This term is bounded, so up to plug in a constant depending on key, you can write this down. But now, this equation, you can apply the theorem for any key less than 1, you have power 1 here in omega, you have a Keller-Osserman condition. So you worsen the equation, but you gain a Keller-Osserman condition. So everything here, what do you have? You have that the u is bounded above, and u star is less or equal than 0. Then apply to minus u, and you get u identically 0. Okay? And any key less than 1 gives, in the volume growth condition, it's 1 plus key minus mu, any mu less than 2. So you actually gain the result. In the case of, what can one say in the case of graphs? Entire graphs in word per product. Well, let me single out 2 examples. Suppose that your word per product, your warping function is convex and grows faster than linearly, in the sense that 1 over h is integrable both at infinity and at minus infinity. Then the only entire minimal graph is the neck of the word per product, provided just a quadratic exponential volume growth condition on the underlying manifold. No further structure. This is related, in the case of the hyperbolic space, h of s is equal to the hyperbolic cosinus is by far inside of this family. So we recover, I mean, we find a proof of Docard-Molozon result completely different and more that applies to more general ambient spaces. And if the warping function increases and grows faster than linearly at infinity and has positive derivative, then there exists no entire minima graph under the same volume growth condition. Okay? Well, and how much time do I have? 5 minutes? How much? Sorry? 11:20. Okay, at 11. 10 minutes? Okay, perfect. The last example to which the theorem can be applied is for, I mean, self-translator. So you are in a product space, and you have a translator with respect to the vector dt. The equation turns out to be this one, because f of u, raise it, but in any case it's 1. And the statement says that under the appropriate volume growth condition, there are no entire graphs which are self-translator for the mean curvature flow that decay, that grow not infinitesimally with respect to r to the sigma. For example, in the hyperbolic space case, sigma is equal to 1, sublinear entire graphs, which are solitons of the mean curvature flow, do not exist. Okay? And again, the result is sharp. In the Euclidean space, you can arrive up to sigma equal to 2, because here you can get a polynomial. It holds for any sigma less than 2, and the result is sharp since entire self-translator exists that grow quadratically. And an example, rotational symmetry example, is the Bose soliton, and there are also some example by Wang, 2011. So let me discuss the proof of the theorem 1. So theorem 1, we will just show that U has to be bounded. How to prove it? Via integral estimates. So it's sufficient. F of t is greater or equal than t to the key, so we place t to the key here, the weight in the lower bound on B, and the structure of the gradient term in here. It's sufficient to prove, to study this semilinear PD on an upper level set for gamma sufficiently large, and prove that if the solution is not constant on this upper level set, it's always non-constant. So if the upper level set is non-empty, then actually you get a contradiction for lambda large enough, for gamma large enough. To this purpose, you isolate the upper level set. The proof splits into two parts. First one is a gradient estimate, is an energy estimate. So the function lambda is just a way to isolate the level sets above. This is the axis of U, let's say, and just a way to isolate the level set omega gamma. And the first point is to achieve an energy estimate on some ball. So this integral, let's keep this. Think of that this is 1 on the upper level set. So it's an energy, this function of the gradient is at most the volume. And then iterate to starting a recursion procedure. Okay? Saying that the energy on a ball of radius r is less or equal than the energy of a ball of radius 2r times a factor that is negative, a negative power, and depends on r to the theta, where theta is the excess k plus 1 minus mu, and we are going to do the case where this excess is positive, so exponential volume growth. And the constant b depends on the upper level set. It grows as the upper level set grows. Suppose that you have these two estimates. Note that for the linear curvature equation, this estimate is trivial, because phi of grad u over grad u turns out to be bounded. But for other operator, actually, our theorem, as it is stated, applies to any phi of this kind, any growth. So any quasi-linear operator, you get the right threshold for the Liouville theorem. Any quasi-linear operator of this kind. And let's see how it works. These ideas, the theorem matches idea coming from a paper by Farina and Serrin with a paper by Pigola, Rigoli, and Setti, and it's a sort of a beautiful combination of the two approaches to get the result. So let's just say how, from the iteration, one can conclude. If you have an iteration, if you have an inductive relation like this, you iterate along powers of a fixed capital R. So you fix R belonging to some interval. We iterate, and we compute explicitly the sum. And it turns out that the logarithm of the energy in a ball of radius R is less or equal than the logarithm of the energy in a bigger ball minus a function that depends on R to the theta. Theta is precisely the threshold for the power of R in the volume growth condition. You just divide and pass to the limit. On one side, you have B times an absolute constant depending just on theta. And on the other side, you have something that does not depend, by our volume growth condition, does not depend on gamma. But B does, since it grows as gamma grows. So for gamma large enough, you contradict this inequality. Okay? And, well, let me say a few words on how to prove the iteration procedure. Well, in the iteration procedure, you have a PDE, you plug a test function. There's not so many things to do. So you isolate the upper level set, put a cutoff that has to be chosen very accurately, and put a power of u, very big power that will be chosen at the end. And the power of the cutoff will be of the order of the power of u. You put in the equation, and you get the right-hand side coming from this part, and you have the usual two terms. But now what you want to do, you want to make this term appear, and you want to make this term appear. So you use order to get rid of this term. And you get a structure like this. Your cutoff becomes multiplied by a lower power, and you have a big power of chi. But now you cannot conclude, as in Kirchhoff's result. You have to choose accurately psi. In which way? You fix a parameter in between 0 and 1, and you want your cutoff to be bounded. The gradient has to be bounded by a power of chi. You cannot do this for tau equal to 1 by Gronval inequality, but you can approach it. Okay? This parameter will be chosen at the end, and it's crucial that it has to be chosen independently of alpha. Okay? Otherwise, the estimate does not work. You put these into, sorry, just very briefly. Here you gain power R to 1 plus chi in the denominator, but on the other hand, you gain power psi to the chi plus 1 over lambda in here. So you have this inequality. Okay? And then you just play a little bit, and you include the weight that appears on the right-hand side. So you divide by R, and you multiply by R to the mu, the denominator. Now you have two different powers, alpha plus omega and alpha plus chi. And since omega is bigger than chi, by the Keller-Osserman condition, you can apply order again to put this into this with the appropriate powers, and you find what remains from applying Holder or Young to this inequality is this guy. And this is very much the energy on a ball of radius 2r. The point is that let me write down again here. The point is that here we have a power of chi, and now we choose tau in a correct way. Remember that power q is of the order of alpha itself. Now, we choose tau in such a way that close enough to 1, in such a way that this quantity is positive. We can do it independently of alpha. So this guy is less or equal than 1. So, and now it's sufficient to say that on the upper level set, localized by this lambda, u is greater than gamma. Put gamma outside. Remove this and put 1, and we get your iteration, your relation. G of r, let's say, is the integral of the ball of radius r, but this is a cutoff of the ball of radius r into the ball of radius 2r, and we have an equation of this kind. Now, at the end, it's sufficient to choose alpha as a power of r in such a way this is kind of 1 to the e. So alpha is 1 to the e times this guy. And since k is of the order of alpha, we precisely have a bound kind 1 to the e, so e to the minus r to the theta, times a constant that grows with gamma. And we have our iteration estimate. Okay? So this proves that gamma cannot grow to plus infinity. Has to stay bounded, so the function is bounded above. Then other related method by using quite different function allows to say that f of u star has to be non-positive. So that's how the proof works. And well, I think that my time is over. Thank you very much.